Hello, my name is Chiamaka Ibeanusi, and this is my Physics Lab 2 report. In this lab, I tracked the motion of a body free-falling and created two computational models of the same experiment that predicts that motion. The first was only affected by gravity, while the second was affected by both gravity and drag. The purpose of this lab is to use our knowledge of Newton's second law to predict the motion of a body dropped from rest that falls somewhat slowly. As you will see from the results, the model with both gravity and drag is more accurate than that with only gravity. The formulas here are derivations of Newton's second law, the momentum principle, which were very useful in creating the computational models. This law was used because the formulas enable us to predict future movements of the body in free fall. The tennis ball is the system, while the surrounding is the rest of the universe, including the wall and the floor. The ball is at rest, so the initial position and velocities are zero. The ball's diameter is 0.067 meters and its mass is 0.0577 kg. I observed and tracked the movement of the ball to generate the graph of its motion, and this can be seen in the following video. The data from the tracker shows the graph of position in the y direction against time, and it is a downward sloping curve. To code the computational model, I used the GlowScript starter code that was provided. The code in the image affects the visual representation of the ball, so I did not edit anything inside. I put in the initial conditions, as mentioned before, and the magnitude of the acceleration due to gravity. For the model with only gravity, my drag force coefficient, which is b, is 0. For the loop, I use my total time of motion as a breakpoint. I put in the velocity and position update formulas as seen and indicated the net force. Then I created the arrow showing the net force acting on the ball, which is gravity, the force of gravity. For the model with gravity and drag, I calculated the value of the drag constant, b, which resulted in the final position and time that was most similar to my experiment. I then made the drag force proportional to the square of the velocity and updated the net force. I also created arrows to show the drag on the ball. This can be seen in the following video. You'll notice that the drag is in an opposite direction from the gravity. The results show that the model that accommodates both gravity and drag is a lot more similar to my experiment than the model with only gravity. Some differences may be due to errors in tracking or recording the video at an angle while performing the experiment, but the results are still quite accurate. You will notice that both the model and the experiment are affected by gravity. This resulted in a downward sloping curve of the graphs. The differences, however, are due to the differences in the accommodation of drag force and experimental and tracking errors, as mentioned before. With these results, you may wonder which model predicts the terminal velocity. The second model, which is affected by both gravity and drag, would demonstrate terminal velocity. This is because terminal velocity occurs when the drag force pointing up is equal and opposite to the force of gravity. This will result in forces cancelling out and having a zero net force on the object. If the object is thrown down, the initial velocity will be higher. The drag force is directly proportional to the velocity squared, as mentioned in the video, meaning that it will be bigger, but the terminal velocity will be the same as the first case. This is because gravity is constant, so the terminal velocity will be constant for a given system, and a given mass, but the time taken to reach the terminal velocity would differ. Thank you for listening, and I hope you learned something new.